Uh, this is first lecture for the course Strength of Material. In the first lecture, we will understand what is the concept of stress and strain. These two words we are going to use throughout the Strength of Material course. In addition to that, we also consider the concept of stress and strain when we study machine design and many more subjects. So in this session we will try to understand what is stress, what is physical significance of stress. If we see a basic definition of stress and strain, so the basic definition says the stresses are nothing but the internal force per unit area. Similarly, strain is change in length per unit area. How we can define these mathematically? For example, if we are having a cylindrical bar of cross section area A and length L, if I am applying a force F on the bar, because of the action of the force there will be some elongation in the bar, and that elongation is defined by del. So my stress, which defined by a symbol sigma, will be force per unit area, and my strain, which is defined by a symbol epsilon, will be defined by change in length divided by total length. But this is very preliminary definition of stress and strain. To have a better understanding, we must understand the physical significance of stress. We must know that why there is a need of stress. So let's understand this with the help of an example. Suppose someone wants to put a vertical bar of material steel, and he wants to apply a load of 100 kilonewton on the bar, and he is interested to find the reaction at this point. So it's a very simple case. If you will apply the law of statics, you know that if I will make the free body diagram of this bar, whatever force the ground will apply on the bar, the similar force will be applied on the ground because of the bar, and definitely in this case the force at this point will nothing but 100 kilonewton. Suppose I want to apply 1000 kilonewton force. Is it possible to get the reaction at this point? Yes. If I will apply the law of statics at every case, whether the force is 100 kilonewton or 1,000,000 kilonewton, I will be able to get the value of reaction at this point. But in real life, do you think that a particular member is capable to sustain a huge load? No. Therefore, there is something else we have to understand. That means this something else is nothing but a concept which tells us that whether the loading is safe for this structure or not. So stress basically tells us that what strength a particular material, a particular structure is able to sustain, or what is the strength of a member, or how much load the member can sustain. So based on this philosophy, we have to understand that why there is a need of stress. Let's take another case. Suppose I am having two bar of a particular material, maybe steel, maybe aluminum, whatever you want to consider. Now let's see here that the one bar is of length L and cross section 5 mm by 5 mm. That means the cross section is a square cross section. The other bar is also of length L, but the cross section size is 8 mm by 8 mm. Now I want to apply a test on first bar. I am giving a loading to my first bar, and I am increasing my load by 1 kilonewton to 2 kilonewton and so on. And what I observe, when the loading value reaches to a value of 5 kilonewton, there is a breakage in the bar. I am just giving you one example that I am having a bar and I am applying load on the bar and I am increasing my load. When the load reaches to a value of 5 kilonewton, there is a failure in the bar. Now, is it okay to tell that the second bar will also get felt at 5 kilonewton force, or the loading for the second bar will be different? Definitely, as the cross section of the second bar is greater than the first bar, then definitely this loading value will also be more than the first bar. That means if I want to tell a failure condition for a particular member, the force value is not a sufficient value. I have to tell something more, which is also dependent on the cross section of the body. And based on that philosophy, the concept of stress evolve, that says that instead of telling the forces which will tell you the safe condition for a particular structure, we say the value of stress for a particular member, and stresses are defined by force by the area. So whatever force, suppose 5 kilonewton force I am applying here, so the stress value for the first bar will be that 5000, that is the 5 kilonewton, divided by 5 into 10 to the power minus 3 into 5 into 10 to the power minus 3, and the unit will be Newton per meter square. So this is the stress value for my first bar. And when I will calculate this, I will get that the total load is coming 200 mega Newton per meter square, or we say mega Pascal. Both are equivalent unit. That means this stress value defines the failure condition of this bar, and for any cross-sectional body which is having the same material will show failure when the stress value will reaches to a value of 5000, reaches to a value of 200 mega Pascal. That means this 200 is the failure condition, not the 5 kilonewton value. We can also check here, as I am showing you, it's a virtual example. Definitely if the second bar is of the same material, and when I will increase my load from 1 kilonewton to 2 kilonewton and so on, I will have a failure which will be equivalent to a stress value of 200. And since I am not able to show you this is experimentally, definitely this second bar will get a failure at 12.8 kilonewton, because when you will apply the force and the a cross section, when you will divide this force with the cross section, you will get a load stress of 200. That the stress in the second bar will be 12.8 into 10 to the power 3 divided by 25 into 10 to the power minus 6, and you will get a same value, that is 200 mega Pascal. So therefore the stress is important to define the safe loading condition for any material of any cross section. Loading is not a sufficient answer. Now, as I said that the definition of stress is not the force per unit area, but I said that the internal force per unit area. So now the second important thing, we should understand that what is this internal force. Why we are not saying it as a simply force per unit area? Why? Because stress tells us the safe loading condition. That means somewhere the loading condition is, external loading condition is not defining the stress, because stress defined by the property, it's a property of the material. Material quality says that the stress value for the safe condition is, for steel is different, for aluminum is different. For example, if I am having two bar, one of steel, another one of aluminum material, both are having a cross section A and A. So what do you think? The failure condition for the steel means the loading for the steel is L1 and loading for the steel is L2. Do you think that both the loading will be same as the cross section is same? No, it will not be same. Definitely we know that steel is able to bear more load as compared to the aluminum. That means somewhere the safe loading condition not depend on the external load. Instead of that, it depends on the internal characteristic or some internal property of the material. So we can understand this philosophy. Suppose I am having a bar and I am applying a force F on the bar. The cross section of the bar is L and the length of the bar is L. Now if there is no deformation in the bar, that means whatever external force I am applying, the equal and opposite internal reaction generated in the material itself, which I defined by a value R here. but actually what is happening inside the material, why this reaction generated, which we can see if we will see the little bit microscopic level. We will find that there are molecules in the body, and molecules are connected to each other with the help of intramolecular force. So when I will apply a certain force externally, each molecule will try to remain in this position, so that there will be an internal force generated within the molecule. That internal force will be equal to the external force until there is not a deformation in the body. So for a condition where the system doesn't show, even though it will get deformed, after the deformation again there will be some steady state condition will reach, and in that steady state condition the forces between intermolecule will again be equal to this external force. Or we say that if the body has a tendency to deform, when I will apply a force F on the body, initially body will show some deformation, after that it will reach to a steady state condition, and finally the system will have a steady state condition where the external force will be balanced by the intramolecular force, and the system will have some deformation. This deformation later we are going to consider in the strain term. So now, because of this intramolecular forces, the equal and opposite force generated within the body, therefore if we are saying that the stress is nothing but the internal force divided by area, so it is true that the internal force will be equal to the external force. So normally we don't talk about the internal force. If we are applying a force F on the body, we directly write that the stresses will be equal to the force and the cross section area. Now we have to understand that what is the concept of strain. Strain is very simple concept, that if you are applying a certain force on a body, definitely if the material of the body has a tendency to elongate, or because of the external force the molecule or the material of the body will have some elongation, and that elongation is maybe very small or maybe more, it depends on the cross section or as well as the material of the body. So strains are defined, it is defined by a symbol epsilon, and the formula for the strain is change in length divided by the original length. Now the question arises whether the original length before the elongation or after the elongation. I am not going in this topic in this session, because in the next topic when we will study the stress strain behavior of a material, that time we are going to see the true stress and true strain. That time I will tell you. But normally when you solve a problem, the problem having that we are having a bar of 10 centimeter, we are applying certain force on the bar. Because of the application of force, there is an increasement of the 2 millimeter in the bar. That means the strain will define by the 2 millimeter divided by 10 centimeter. You can convert the unit later on, but it is just an example that how to calculate the strain. After understanding the concept of stress, physical significance of stress, and then what is strain, now we have to understand that what are the different types of stress we deal in our normal designing of structures. Normally in the design of mechanical components, there are three types of stresses encountered normally. One is the normal stress, second one is the shear stress, third one is the bearing stress. Now we have to sequentially understand what are these three stresses. The three stresses can be understood with a concept of forcing on a bar or on a plate. So here I am explaining three stresses parallelly. First we see the normal stress. Normal stress are very simple stress. We normally study that if we are having a cross section, a body of certain cross section A, and we are applying a normal force, or the force is acting normal to the cross section of the body, or if I will say that if the force value go beyond a certain condition, because of these kind of forces, the section which going to be fail is like this cross section. So that means whatever the cross section which is giving a resistance against the external load is normal to the load. or I can say that the force acting normal to the surface, which is going to be fail in all these cases, the stress generated in the body defined by the normal force by the cross section area, and such stresses are known as the normal stress. Second type of stress, which is shear stress, can be understood by this example. Here I am showing you two plates A and B parallelly connected with the help of a rivet, and I am applying a force F on one of the plate. The other platelets having a fixed connection. So because of the fixed connection, definitely there will be equal and opposite force F here also. Now you see there are two conditions may arises. One condition is that if I will see the plate A here, all the cross section which are responsible or which are giving a resistance to the external force are perpendicular to the force. That means whatever stress generated in plate A or in plate B is normal stress. On the other hand, if I will see the condition of the rivet in such external loading condition, what sort of failure occur in the rivet, or what kind of forces are there, and which area is basically responsible to maintain the rivet in its present shape. So we can see here that the cross section which may get fail because of the external loading will be this cross section. This cross section means what happened? The top part of the rivet may go with this plate and the bottom part of rivet may go with this plate, and there is a tearing or a breaking of the rivet from this point. If the rivet will fail from this cross section, if I will see the three-dimensional view, I will find that the circular cross section of the rivet is responsible to maintain the shape, or I would say that this cross section will have a failure because of this external loading. So in this case, the loading is tangential to the area which is responsible or which is giving a resistance. In that case, whenever we are having a tangential force, that defines the shear stress, and shear stress is defined by a symbol tau. So this is your shear stress. When we will see different problems, the concept will be more reinforced, but here you should have a basic understanding that when we call a stress normal stress, when we call a stress shear stress, the third type of stress is bearing stress. Bearing stress can also be understood by the same formula. Now let's understand three conditions. One is the normal stress failure. Suppose bar or the plate is strong, so there is no normal stress failure. Second failure may be the shear stress failure. Now again assume that the rivet is so strong, so there is no tearing off of the cross section. Then what could be the third kind of deformation occur in your system? So if we will see carefully, we will observe that if I will take this small portion diagram here. So this small portion diagram is here, which is having a semicircular hole here, and there is a connection or interfacing between the rivet surface and the surface of the plate. If the material is not so hard, and because of there is mutual reaction, the surface get distortion. Now there is no tearing failure in the plate. Now there is no failure in the rivet. Instead of these two failures, there is a third failure which is having the deformation in the surface, and because of this mutual reaction, the surface no longer remains semicircular or become oval type or some different type. The failure may occur in the plate, may occur in the rivet. If the rivet material is softer than the plate material, definitely the rivet material will first show the bearing failure. So such bearing failure normally considered when we are having two surface in contact or the circular surface. These are generally observed in pins, bolts, rivets, etc. So what happens and how we can mathematically write the formula for such stresses? If we will see here the loading condition, suppose this is your semicircular section, I am putting this value and I am applying a normal force because there will be mutual reacting forces at this place interface. All the forces are acting on this surface, but if you will see carefully, not all the forces are not perpendicular to the surface of the plate. at the same time, all the forces are not tangential to the surface of the plate. However, the forces are having some inclination when we have tangent on the surface of the circular part. So if you want to calculate the stress, you cannot use the simple force by the cross section area. Instead of that, your force will going to be act on an equivalent projected area. So for this particular area, the projected area will be a rectangular body if the thickness of the plate is defined by T and the diameter of the hole is D. So this projected area will be T into D. So my bearing stress written as bearing stress will be the force between the two surfaces by the B projected area. So now we have a basic understanding of three different stresses as well as what is the concept of stress and strain. So now in next class we are going to see the stress strain diagram as well as the true stress and true strain. Later on we will see the stresses on the oblique plane and the Mohr circle diagram and so on. Thank you.